We're going to continue solving systems, and this video is titled Dependent Systems, so we're probably going to see some dependent systems, and we'll see what to do with those. Alright, so we're going to begin traditionally by writing the augmented matrix. So 0.3, negative 0.1, and then minus 2. Now we have to mentally do this or rearrange this, so this would be minus 3x plus y is equal to 20. So it'd be minus 3 and then 1 and 20. Okay, so then we can maybe see what's going to happen already, but what we end up getting is if we take 10 of row 1 and add to it row 2, putting that into row 2, we're going to end up with 0.3, 0.1, or negative 0.1, and then negative 2 and zeros all in the second row. Okay, so in terms of using anything further here, it's not going to be useful. I can't do reducer or echelon form, for example. So all I have to do here is translate this back into an equation, so do back substitution. I've effectively done Gaussian elimination. 0.3x minus 0.1y is equal to minus 2, and I'm going to solve for one variable or the other. I'm going to choose to solve for y in this instance, so 0.3x minus 2 is equal to 0.1y, and then consequently y is equal to dividing this by 0.1 is 3x plus or minus 20. Okay, so then in terms of my solution set, I can say the solution set is, and then this one, it's going to be in terms of a variable. So normally I would write x and y, right? But instead of y, I have the expression 3x minus 20, and I'm going to write that expression in place of y. Okay, so that's all the more we can do here. Let's see how the next two shake out. Alright, so here I have another one. I'll write it in matrix form first. So 1 minus 3 minus 17 are the coefficients, and I have minus 17 on the other side, minus 2, 7, and 38 are the coefficients for the second one, and then 40 on the other side. Alright, so kind of continuing by Gaussian elimination, I want to get this 2 gone, so that's in row echelon. And so then to do that, I'm going to do 2 row 1 plus row 2, and put that into row 2. Okay, and I have 1 minus 3 minus 17, and then minus 17. And if I then hold all these numbers in my head, so 0, 1, 4, yeah, because that's 34, negative 34 plus 38 is 4, and then similarly here I'm going to end up with 6. Okay, so that's all the further I can go. I guess I could, try and knock out this 3 if I wanted to. Actually, why don't we? Let's do Gauss-Jordan. Okay, so we're going to try and knock out this 3. And to do that, I need to do 3 row 1, or row 2 rather, plus row 1 into row 1. Okay, so second row remains unchanged, 0, 1, 4, and 6, 1. And now I have to take 3 of this and add to that, so that's going to be a 0. And then 3 of this, add to that, minus 5. 3 of this, 18. 18 minus 17 is 1. Okay, so then from here, I get the equations. X minus 5y is equal, or 5z rather, is equal to 1. And y plus 4z is equal to 6. Now what I'm going to do is I'm going to solve each equation for x and then leave it in terms of z. So x is equal to 5z plus 1, and y is equal to negative 4z plus 6. Consequently then, I can write the solution set as, okay, normally you would write an x value, a y value, and a z value, right? But instead of x, I have the expression 5z plus 1. Instead of y, I have the expression minus 4z plus 6. And that's all there is, okay? Alrighty, so a couple different examples. The first one I ended up just using Gauss-Jordan, or Gaussian elimination, and using back substitution. With this second one, I did Gauss-Jordan, but that didn't solve it fully, so I had to do back substitution to finish it off. Okay, so even with Gauss-Jordan, you might have to use back substitution. Alright, for this next one, I want you to pause the video, try it out, and resume the video when you get stuck. Alright, so I'm violating the rules here a little bit, I get that, but bear with me. Okay, so normally I want a leading 1, I have a leading 2 instead, so I'd have to, take 1/2 of the first row, but I digress. I noticed that all these numbers seem to be closely related, so I ended up taking -2 row 1 plus row 2, putting that in row 2. That wiped out the second row. Did something similar with -10 times row 1 plus row 3 for row 3. That knocked that row out too. So I'm left with this singular equation of 2x minus 3y plus 5z is equal to 3. So then the question is, what do you do with this, right? The answer? Well, you're going to have what we call 2 free variables. Okay, you can solve for one variable, but that's going to be the best that you can do. For instance, if I solve for x, I'm going to say x is equal to, so 2x is equal to 3y plus, minus 5z plus 3. And then going a step further, divided by 2, x is equal to 3 halves y minus 5 halves z plus 3 halves. And that's the best that you can do. Okay, now, in terms of writing your solution set, okay, how in the world do you write your solution set? Okay, this is still a dependent system. But it's dependent instead of on one variable, it's dependent on 2 variables. Okay, so you would normally write x, y, and z, right? Well, the only thing that we were able to figure out some information for is x. So instead here, you're going to have 3 halves y minus 5 halves z plus 3. Okay, and otherwise this would be your solution set, and technically you would write something like this where y and z are real numbers. Geometrically, this is an example of where you have 3 parallel planes. Like, they're not 3 parallel planes, they're 3 planes that are parallel and exactly the same. They're just multiples of one another. Okay, so this is a little wonky, but we can still write the solution set. Okay, just using 2 free variables.